Myself, Dr. Anish, Professor of Department of Radiology. Today I'll be talking on basics of radiation. That is one of the first competency in the Department of Radiology as per NMC. So this is the SLO, Specific Learning Objective, I expect from the student. That is, at the end of the session, student must be able to describe production of X-ray and interaction of X-ray with the matter. And they should be able to enumerate the effect of X-ray on human body, and also to describe some basic measure to be taken to protect patients as well as radiation workers from harmful effects of radiation. Some brief history about the X-ray. The X-ray was discovered by William Conrad Röntgen in the year 1895, November 18. Actually, he was working on cathode ray tube. So incidentally, he detected a glow in the luminescent screen which was kept some feet away. So he coined the term, that unknown radiation, as X-ray. So he was awarded the Nobel Prize for this discovery. This is the first X-ray ever taken of a living human. This is the X-ray of William Röntgen's wife, Anna Bertha Ludwig's hand. So this was her expression on seeing the X-ray. Oh my God, it makes me somehow feel that I am looking at my own death. So what is X-ray? X-ray falls under the group of electromagnetic radiation, like other electromagnetic radiations like radio waves, gamma radiation and visible light. So what are the properties of X-rays? They are electromagnetic radiation and highly penetrating invisible rays. They are electrically neutral. They travel in straight line with the speed of light. They cause ionization and produce chemical and biological changes. So about the production of X-ray. X-ray is produced in X-ray tube. In X-ray tube there is a cathode and anode end. So when the potential difference of the electricity is applied, the electron will move from the cathode side. There will be filament on the cathode side. From there, the electron will move towards the cathode, and when it hits the cathode, there will be tungsten target on the cathode. So then there will be production of X-rays. So the tube consists of a glass envelope and the cathode and the anode. So this is how the X-ray is produced. The fast moving electron will hit on the anode, interacts with the atoms of tungsten anode, and then the X-ray is produced. I'll be discussing in detail how the X-ray is produced. So these are the types of anodes. The initial days it used to be a stationary anode. What happens is the electron will be bombarded on a fixed spot, so thereby it causes heating and it causes early degeneration of the anode. So nowadays what we have is rotating anode. So like in this image, you can see there will be rotor, and the anode will be rotating. It has a beveled edge and it rotates at the speed of 3000 to 3500 revolutions per minute. So the heat is dissipated along the circumference. So you can see the same on the tube, actual X-ray tube over there. These are some accessories in an X-ray setup. That is the yellow one is the X-ray tube. And then there will be a collimator which limits the amount of radiation, or you want only the particular area of interest only will be exposed. And then there will be a patient, and behind the patient there will be a grid. So both the grid and the film will be placed in a bucky. So the role of grid I'll explain later. So this is the basic structure of the X-ray setup. So before going to the production of X-rays, the physics of production and also the interaction, just we need to understand the basic structure of atom. So an atom is made up of a nucleus which has proton and neutron, and an orbital electrons which are negatively charged. So these electrons are placed in orbits, or also called as shells, in K, L, M, N in that order. The shells have a limited electron capacity. Like K shell will be having 2 electrons, followed by 8 electrons in L shell, and so on. So each shell has a specific binding energy. The closer to the nucleus, the binding energy will be more. It will be more tightly bound, and electrons in the outermost layer are loosely bound. So they are called free electrons. So let us discuss the generation of X-ray. So there are 2 types of radiation in the production of X-ray. The first one is the general radiation, also called as Bremsstrahlung radiation, and the characteristic radiation or K-shell radiation. The general radiation or Bremsstrahlung radiation. Bremsstrahlung means in German it means the breaking radiation. Like you can see the image, the first image and the second image if you follow. So there is a nucleus of the atom, and the electrons coming from the cathode tube, if they are closed, passing near to the nucleus, then because of the positively charged nucleus, the electron may get deflected, and also the velocity will come down. So that is why it is called breaking, or there will be slowdown of the speed of the electrons. So that energy lost is produced as a X-ray photon. So that is how X-ray is produced as per the Bremsstrahlung radiation. So in an electron gives up only part of its energy when it moves close to the nucleus. The single electron may undergo many interactions. So after the first interaction, even though its energy is reduced, it may interact with another nucleus, and so on. The energy of each electron striking target is different, because energy may slow down, so the striking energy will be different. So due to the fact the radiation produced due to Bremsstrahlung radiation will have photons of varied energy, and thus varied wavelength and varied energy. So the 99% of this interaction, Bremsstrahlung radiation, are given off as heat. So the next method by which X-ray is produced is the characteristic radiation. So there will be interaction with the electrons. Initially, Bremsstrahlung, there will be interaction with the nucleus, whereas here what happens is the fast moving electron coming from cathode tube will hit the K shell or the inner shell electrons, and because of which the K shell electron will be deflected or thrown out of its orbit. So the next, that is an unstable atom. So what happens is the outer shell electron will move into the inner shell to fill the gap. So like let's say take the example of tungsten target, because that is the target used in X-ray tube. So the K shell binding energy of tungsten is 70 keV, and L shell, that is the loose outer shell electron, is only 11 keV. So thus the energy of photon produced is equal to the difference between the binding energy of K shell and L shell, that is 59 keV. So this energy will be same for all the interaction of characteristic radiation, because the difference of K shell and L shell will be the same for a particular atom. So that is why it is called characteristic radiation. So this radiation is produced only when the energy of the hitting electron is greater than binding energy, then only it can throw it out. So there is just for comparison, I am putting this slide. This is the interaction, similar kind of interaction of X-ray or X-ray photon with the matter, with the patient body and the atom in the patient body. So here also what happens is when the radiation or the X-ray photon hits on the inner K shell, it will be kicked out, and there will be moving of outer shell electron into the inner shell. So and then there will be production of X-rays. This radiation is will be the cause for scattered radiation. One of the causes. There are other causes also. I will be dealing with that later. So let us see the differences between the characteristic general radiation and characteristic radiation. So the general radiation of Bremsstrahlung will have heterogeneous energies and wavelength, whereas characteristic only single energy. So as we discussed, the characteristic radiation will be characteristic of a particular atom used. So next is interaction of X-ray with the matter. Now the X-ray is produced. So what happens when the X-ray is interacting with the matter? So there are 5 types of interaction: coherent scattering, photoelectric interaction, Compton interaction, pair production, and photo disintegration. Let's see one by one. The first is coherent scattering. Here when a low energy radiation encounters an electron in an atom, that atom is set into vibration. So when the electron return to the resting state, they give up the photon with the same wavelength. So this is the only interaction between X-ray and matter in which there is no transfer of energy and thus no radiation, because there is no loss of electron. It is set into motion and it comes to rest. So the same energy photon is produced, but in a different direction, so leading to scattered radiation. So radiation undergoes a change in direction without change in the wavelength, hence it is called unmodified scattering. So this is the only type of interaction that does not cause ionization. It contributes to less than 5% and it is insignificant. And it may cause film fog. I will explain that later. So the next important interaction is the photoelectric effect. So it is similar to the characteristic radiation. So you can understand with the image, the inner shell electron is kicked out and there will be outer shell electron moving into the inner shell. So this is called as photoelectric effect when the photon is sitting on the matter. So electron which is ejected by photon is called photoelectron. So in a photoelectric effect, it is an ionizing interaction. It yields a characteristic radiation, a negative ion and a positive ion, that is an atom deficient of electron. So next, the most important interaction of the X-ray is the Compton scattering. So here what happens is the incident X-ray photon will hit on the free electron, the outer shell electron, thus displacing it out of the atom. So still what happens is the incident photon keep on moving even though it may deflect to some extent. So the difference between photoelectric effect is that incident photon retains part of its energy and travels in new direction as a scattered radiation. Whereas in photoelectric effect, most of the energy is lost. So here you can see with this image, this is from this arrow, this is the electron which is hitting the target, the photon which is hitting the matter. Suppose if the energy is 75 keV and based on the deflection, there will be this is the resultant energy of the deflected or the scattered radiation. So if you can see, even at 90-degree deflection, most of the energy is still retained. So that is a 75 to 66, almost 90% energy is still retained. So this is the major problem in radiology. So this is the cause for scattered radiation is an issue with radiation protection. So almost Compton scattering, almost all the scattered radiation that we encounter in diagnostic radiology comes from Compton scattering. Problem with Compton scattering is at narrow angle of deflection, this may retain almost all its energy. So this may create a problem when it has an excellent chance of reaching the film and causing film fog. Film fog is the deflected, scattered electron falling on an unintended location on the film. Thereby the resolution of the clarity of film is lost. This reduces the quality of the film. Health hazard is because even after the photon has been deflected 90 degrees, still it retains most of its energy. So to overcome this, what we have is known as the anti-scatter grids, also known as a Bucky-Potter grid. So here after the patient and the film is the lower one. So we place a grid made up of lead. So what happens is that you can see that after the patient there will be a lot of scattered radiation. This grid will limit the scattered radiation going into the film, so thereby maintaining the quality of the film. So there are last two interactions which are not very important because it needs very high energy, which is not used in diagnostic radiology. So there is a pair production. When high energy electron interacts with the nucleus of an atom, the photon disappears and its energy is converted into matter in the form of two particles, that is electron and positron. I'm not going into detail. So there is a photo disintegration. So this interaction also not of importance in diagnostic radiology. So when X-ray strikes on the patient or the matter, so what are the effects? So some of the X-rays are absorbed, some are deflected or scattered, and some pass through the patient. So let's see what are the effects of ionizing radiation on humans. So it is broadly classified into stochastic effect and non-stochastic effect. Stochastic effect. Here the risk increases with the radiation dose, but severity does not depend on the magnitude of absorbed dose. In the sense, so even if high radiation is there, some patients, some people may not have that effect. So that's why it is called as all or none phenomenon, like the cancer carcinogenesis and the genetic effects. So here some of the specific cancers associated with ionizing radiations are leukemia, multiple myeloma, breast cancer, lung cancer and skin cancer. So now the non-stochastic effect. Here the effect of radiation exposure is defined as somatic effect that increases in severity with increasing absorbed dose. That means even at lower dose there will be some effect on the cells of the body, and the severity increases with the increasing the dose. It is not all or none phenomenon. Like blood changes and decreased sperm count, these are all examples for non-stochastic effect. So this is a tissue sensitivity. So it is proportional to the rate of proliferation of the cells. More proliferating mitotic, the cells are highly proliferating, are more sensitive, like blood forming organs, reproductive organs in the decreasing order, and the least sensitive is the CNS. So few words about radiation protection. First about the protection of the patient. So in the X-ray tube, after the X-ray tube, what we can use is what a standard X-ray setup will have is a filtration. Usually there will be an aluminum filter. So what is the use is, in the first image you can see there are, other than useful electron, there are few low energy photons which are shown as a green color. So we can limit this low energy unwanted electron from reaching the patient, thereby reducing the radiation by using a filter. And X-ray beam restriction. So we can use like cones and cylinders which can limit the field of view, or we can focus on the area of interest. There are few more things, like one important is the time. So least time spent near the source of radiation, less radiation received. So this is the importance of time and the importance of distance. So greater the distance from the source, less radiation received. So there is something called as inverse square law. The dose is proportional to the inverse of the square of the radius from the source to the radiation worker of the patient. So if you double the distance, the radiation dose will reduce by the factor of 4. That is the inverse square law. And next important thing is shielding. So behind shielding from the source, less radiation received. Like we use lead for shielding. So this is some of the radiation protection equipments, devices which we use in day-to-day practice. So there is the golden gonad shield for patient, thyroid shield, and lead apron, lead goggle, and lead gloves for the radiologists who are working with radiation, radiologists and all technicians. So this is thermoluminescent dosimeter. So there are different dosimeters before, but now currently we are using TLD or luminescent dosimeter. So this is used to measure the radiation received by the radiation worker over the period of time. So this will be assessed by the Barb Atomic Research Center. So in this, the method is thermoluminescence is the property of certain material to emit light when they are stimulated by heat. So based on the amount of radiation received by this material, the luminescence will be different. So they can quantify the amount of radiation received by the worker. So it is made up of lithium fluoride, lithium borate, calcium fluoride, calcium sulfate. These are used to make TLDs. So just to show the radiation signage, which is important in radiology, if you visit radiology, you will see these signs. So this is suggestive of ionizing radiation.